Okay, so today we're going to talk about vector spaces over the complex numbers. And also Hermitian matrices. So vector spaces over complex numbers. Inner product in those spaces, you will see that there are many interesting things. And then eventually Hermitian matrices. So, so here's some very interesting things. So a complex vector space has a definition. Identical to that of a real vector space, with the exception that we scale vectors by complex numbers and not just by real numbers. The standard example of a complex vector space is C to the n. Okay, so C to the n is defined as all column vectors Z1, Z2 up to Zn, with Z sub I being now complex numbers. And of course, the addition, so you add two such vectors, by adding the corresponding coordinates. And then you scale vectors like this, where lambda here can be a complex number. So just to give you an idea, just to make sure that we are on the, so how do you scale I times 2, 3 minus 2i? You're going to do 2i, and then it will be minus 2i times I will give you 2 plus 3i. Okay, and we just scaled our vector by the number I. So we have a, so everything that we have said, meaning you can solve systems over the complex numbers by just mimicking the Gauss elimination method. You can define determinants. You can pretty much do everything there are some things that are going to change. So, for example, when you find the eigenvalues of a matrix, you will see that you can always find as many eigenvalues as the degree of the characteristic polynomial, meaning the dimension of the matrix, which is not something that you can say about real numbers. For real numbers, you can get polynomials that do not have as many roots as you would expect them to have. And this has an immediate and very amazing consequence. Every complex square matrix is similar to a triangular matrix. Not a diagonal one. Still, you will have matrices that cannot be diagonalized, whether, I mean, we already saw real matrices that have enough eigenvalues and could not be diagonalized, and such a matrix would also be an example of a complex matrix, because the real numbers are a subset of the complex numbers. Anything you say about the real numbers pretty much carries over to the complex numbers, not vice versa. So if you say something about complex numbers that is not true for real numbers, but if it's true for real numbers, then it's true for the real numbers being seen as a subset of the complex numbers. So we have something, we have already here a property which is not true for real numbers. So we can do more things with the complex numbers. And we would like to see how this is possible. And we would like to also bring in the inner product in this whole conversation, and you will see why. So now, how do you define the inner product between two vectors with complex coordinates? So what's the inner product here? And this is where things start changing a little. And you know, in the beginning they might seem a little annoying. So I'm going to take the products of the corresponding coordinates. So the first coordinate of the first vector with the first coordinate of the second vector, the second coordinate of the first vector with the second coordinate of the second vector. So I'm going to multiply z sub I times w sub I. I would like to also add them all together. If I do that, then what I have looks precisely like the inner product for the real numbers, but there's a very significant difference that I'm going to impose now by asking that for the second vector, I'm taking the complex conjugate. Meaning, if we want to give the definition of an inner product in a complex vector space, then we actually give the following properties, which are a little different than, which have this little difference from the properties of a real inner product. So if V is a complex vector space, sometimes we also say a vector space over the complex numbers. Then an inner product is a function from V cross V to C, denoted like this. So you put the two variables where the dots are, such that So the first thing is pretty much the same if you take the dot product of a vector, or if I want to give them with respect to the same order that I gave you the properties in the case of the real numbers, then if I take two vectors and I take their sum and then the dot product with the second vector, then I can distribute the inner product like so. And if I scale, look, here's where it gets a little interesting. Then it's fine as long as I do it for the first coordinate. But here's the thing. The inner product is not symmetric anymore. So the inner product of a vector with another vector, if I change the order, then they're not equal anymore. They're complex conjugates to each other. I remind you that when I talk about conjugation in the context of complex numbers, I mean that I flip the sign of the imaginary part. I flip the sign of the imaginary part. And of course, the other properties have to do with the positive definiteness, so that the inner product of any vector with itself is greater than or equal to 0. And the only way that the inner product of a vector with itself is equal to 0 is if and only if the vector is the 0 vector. Okay, and now you have the properties for complex numbers, and those properties have a very substantial different consequence. So what you have is that if you have a scalar on the second coordinate, like so, you cannot just extract it in the beginning. You in front of the vector, you need to actually put the complex conjugate in front. Now, of course, you may ask, well, how is this justified? Sometimes it's an interesting thing to see this theoretical justification. So you get, I have no clue how to extract it from the second coordinate. So that's why I flip the two vectors. But the moment I flip the two vectors, I get the complex conjugate, right? But now that I have lambda on the first coordinate, then I can extract it, but it still stays over under the complex conjugation. It is true that the complex conjugate of the product of two numbers is the product of the complex conjugate. So this becomes lambda times the inner product of W with U. And eventually I can flip it back and I have lambda conjugate times U dot W. And that's how this property is justified. That's why sometimes we say that the inner product in the case of real numbers is bilinear. Okay, let me mute everyone. I'm sorry about this. So that's why we say that the inner product in the case of complex numbers, of real numbers is bilinear. In the case of complex numbers, it is 1.5 linear. Sometimes we say 1.5 linear. So it's linear with respect to the first coordinate and half linear with respect to the second coordinate. I think there is another word which is called sesquilinear. I haven't used this word for a while now, but sesquilinear. Anyhow, we won't need to know this word. But I would like to explain. I mean, for me, I vividly remember the very first time that I saw this inner product in the case of complex numbers, and it really bugged me. I looked at it and I'm like, why do people do this to themselves? Why don't they take, W I instead of in the formula instead of the complex conjugate? Why don't they just make it look as simple as the real case? And there is a very simple reason why this wouldn't work. And let me show you why. So let's say for the moment, for humor me here and say that you decided to make the inner product to be sum from I equals 1 to n of z sub I times w sub I, right? Imagine for a second that we said, okay, so let's do it this way. Then what would happen when you took the inner product of the vector I comma I by itself? Now you will see what the problem is. If you did this and you didn't have the conjugation on the second term, then that would give you I squared plus I squared, right? Now what is I squared plus I squared? Ooh, it's -2. So all of a sudden, the inner product cannot be used in order to define a length. Unless you're willing to allow lengths that are negative numbers, and of course, at this point, you might say you're out of your mind now. No, actually, it is a consideration. It is something that one could possibly do. But unless you want, in very, very special cases, so there are inner products that are indefinite inner products, as we call them. But the reason we use those things is are completely different, and sometimes they do stem from application. So, for example, in the Lorentzian space, for example, we use inner products that have this kind of seeming defects. But the bottom line is that at an elementary setting like the one that we have in front of us, we really want to use inner products that behave as nicely as possible and actually define a length for the corresponding vectors. So the length, the norm, if you like, in our case, is going to be, again, what it was in the real case. So if you have a vector, its norm is simply going to be the square root of the inner product with itself. So this formula is still going to hold here. Okay, so if you want all of these things to happen, then you'd better define your inner product this way. Questions? So you will see that complex conjugation is going to be a very important component of what we're going to do from this point forward. Questions? Okay. So now, what's the story here? Pretty much, we're going to define a new, with every operator, a new matrix, if you, a new operator, a new, and in the case of that we interpret operators through matrices, a new matrix, if you will, by the property that A U inner product with V is U A star of V. So this is the usual notation that we have here. And this A star ends up being the transpose, the complex conjugate of the transpose. So again, let me give you a simple example. So let's say that the matrix A is this, 2 plus I, 2I plus, or 2i simply, 1 plus I, 3. Okay, let's put all sorts of numbers in the mix. Then what is A star? So A star is a little interesting here. So first of all, every number is going to get conjugated. So the complex conjugate of 2 plus I is 2 minus I. The complex conjugate of 3, since 3 is real, its complex conjugate is going to be itself. And now, since we're also taking the transpose, this 2i should come here, but it should be replaced by its complex conjugate, and the complex conjugate of 2i is negative 2i, and the complex conjugate of 1 plus I is 1 minus I. So that's this adjoint matrix. So sometimes we call this adjoint. Okay. So let me give you an example to yourself. So 3 plus 2i, 1 minus I, 2 plus 4i, 5, 6i, 2 minus 3i, I, 0, and 7. Could you please find the adjoint of this matrix? Could you please find the adjoint of this matrix? It's going to be a 3 by 3 matrix. Could you please find it? Okay, so let's see together. So we begin by taking the conjugates on the diagonal. So you will have 3 minus 2i, you will have minus 6i, you will have 7. And then you flip everything else with respect to the diagonal, and you take their adjoints at the same time. So you will bring this over here, 1 plus I, though, 2 minus 4i, 2 plus 3i, and this will become 5, will stay as 5. This will become negative I, and this is 0. And that's it. Okay? And then once you define the adjoint this way, then you have this. And basically, our goal here will be to look at self-adjoint operators. So an operator and the corresponding matrix for that matter is going to be called self-adjoint if A is equal to A star. Okay, so for example, any real matrix is self-adjoint as long as it is symmetric. And so you have that an example, for example, would be everything on the diagonal should be real. And then whatever you have off the diagonal should be there should be a symmetry with respect to the complex conjugate. So if you have, let's say, 1 plus I here, then you should have the complex conjugate of that on the other side. So this is an example of a Hermitian matrix. So this self-adjoint operator, and then the matrix itself is called Hermitian. Okay, so this is an example of a Hermitian matrix. The self-adjoint is usually attached as a term to the operator, to the linear map. So the corresponding linear map will be called self-adjoint. And the matrix of a self-adjoint map will be a Hermitian matrix. Okay. And here comes our big theorem for today. The eigenvalues of a Hermitian matrix are real. Please note the following. The eigenvalues are real. The eigenvectors do not have to be real. They do not have to have real coordinates. And it is diagonalizable. So every Hermitian matrix is diagonalizable. It turns out that we can actually weaken this we can give results for more general matrices that actually commute with their adjoint matrix. They're called normal matrices, and but we're not going to go down that path. So we're going to just study this, and here we have a very nice consequence. So the consequence that we get here, sometimes people like to call this corollaries, is that every symmetric real matrix is diagonalizable. Okay. So I would like us to take a break now. And when we come back, we will see an example of how we diagonalize a Hermitian matrix. And you will see that that's pretty much the only thing that I want you to know from this context. I'm going to mention at the end of the lecture that we can also have a Gram-Schmidt orthonormalization method. One has to be a little more careful with the formula, and I'm going to show you how. And but in terms of the scope of this course, I just want you to know how to diagonalize a Hermitian matrix. That's all. And we're going to see an example right after the break. Okay. Recording. Okay, let's give an example now of diagonalizing a Hermitian matrix. So first of all, are there any questions so far, please? Okay, so here's how I'm going to give this problem. So give a diagonalization equation. The work that I'm going to do is exactly the same as with the real numbers. So let's give ourselves the following matrix. So let's give 1, 2i, 1, negative 2i. Okay, these are the kind of matrices that I will give you also on the exam. I mean, it's not going to be some 3 by 3 matrix for sure. It's going to be just a 2 by 2 matrix. And so give a diagonalization equation for this matrix. So the first thing that we need to do is find the characteristic polynomial. So P of L is going to be the determinant of lambda times the identity minus the matrix. Let's call this matrix A. And this is going to be what? Lambda minus 1 minus 2i, lambda minus 1, right? And when you multiply out, you will get lambda minus 1 squared. And now you have minus negative 2i. Let me show this in detail. I mean, it's pretty straightforward, but let me show it in detail. So you see here, I times I is negative 1. I times I is negative 1. And with a negative sign, that is plus 1. So this whole thing is 4. So what you get is actually lambda minus 1 squared minus 4. 4 is the same thing as 2 squared. And the reason I'm doing this is because there is a very simple identity here, the difference of the squares identity, which tells you that this is lambda minus 3 times lambda plus 1. Right? So far, so good. So our eigenvalues are 3 and negative 1. Right? So this means that the diagonalization equation will look like this. It will be A, P, P to the negative 1. And what you're going to find is, let's put them in this order, 3 and 1, like so. Maybe you could do 1 and 3. It's, as you know very well, it's the same thing. Right? And so let's work first with lambda equals 3. So for lambda equals 3, what do? We write down our matrix. Which matrix? The one that you have inside the determinant. So what does it look like? It looks like 2 minus 2i, 2i and 2. And of course, you write it as an augmented matrix because you want to find its null space. Okay, is everybody with me? I mean, you will see it's identical to the process that we had. If you like, it's a review of the process that we had for real numbers. It will be just a nice opportunity to do it for complex numbers. So we will have to just do everything in the presence of this imaginary unit, pretty much. Right? Okay. So what do we have? I'll, as usual, I will create my pivotal element. So 1/2 row 1. So you see how one of the things that I'm trying to advocate throughout this course is try to be very precise and very systematic about how you apply these methods. And that's why the theoretical part of this course is as important as the practical one. And that's why I insist on the theory of vector spaces, which gives us the right framework. And then we need to multiply by negative 2i and add it the first row and then add it to the second row. And that is going to give us 1, negative I, 0, and 0. Now here's where we have to be careful. Can anybody tell me how much is negative 2i times negative I? How much is negative 2i times 2i? It is -2, very good. It is -2, so +2 is 0 here. And then we get 0, and that's it. That's row echelon. Okay, now we put it back to our equation, and we have, so this tells you that this is going to be free, right? So this is free. So x minus iy is equal to 0. X is equal to iy. So your vector will look like y, iy comma y. And if you set y equals 1, you get the eigenvector I comma 1. So here's the first eigenvector, I comma 1. I comma 1. Okay? Now, here's what I would like to do. I would like to give you a few minutes, and I would like you to try to do the job for lambda equals 1 yourselves. Okay, so for lambda equals -1 yourselves. Why did I get y equals 1? Because these are all the eigenvectors. I simply want one of them, right? So because remember, when you make up your transition matrix, you put the eigenvectors as columns. So the one that I chose is I comma 1 because it's especially simple compared to everything else here. Okay. Any more questions? Okay, so please take a couple of minutes to try to do the case lambda equals -1 now. Okay, why don't we do it together now? So if we consider lambda equals, actually, let me use the same ink. Oops, I said the same and then. So if we consider lambda equals to -1, then what matrix do we get? We get -2, -2i, 2i, -2, and then zeros as usual. So we're creating our pivotal, -1 half row 1, and that will give us 1, -i, 0, 2i, -2, 0. Now, we want to eliminate that 2i from the bottom, so we do -2i times row 1 plus row 2, and this gives us 1, -i, 0, and -2i times -i is -2i times -i is -2. Sorry, there's something that I don't like here. That shouldn't have been -2. What is going on here? You're saying it should be, yes, you're absolutely right. Thank you. Thanks for saving me here. That's exactly right. That's I. Thank you. Because you need to have the other one eliminated. Why do you need to have this number 0? Why should I have expected to get a 0? Because if you don't get a 0 here, if you get some non-zero number, then eventually you can make that pivotal. You're going to have two pivotal elements, and eventually the null space is going to consist just of the 0 vector. That cannot happen. That cannot happen. Okay, that's why I was so disturbed to see that this was coming up to be non-zero. But now it's all good. And so we got 0 because if you multiply -2i, if you multiply -2i times I, that gives you 2, right? Why is that? Because I squared is -1. -1 times -2 is 2. Plus -2, that's 0. Okay? I know that it's, if you have not done arithmetic with complex numbers before, it might look a little, a little awkward in the beginning. But wait till you hear what I have for you in the end, and then you will see. Anyhow, x plus iy is equal to 0. That's our equation. And again, this is going to be free. The y is going to be free, which tells you that x is equal to -iy. And what we get is -iy comma y. And again, I'm setting y equals y equals 1. Could set y equals -1, I guess. I don't know. I mean, y equals -1. Just to tell you, the reason I'm setting y equals -1 is to tell you that it doesn't really matter. Just set any number other than 0. And you will get I comma -1. Okay. And this is your second vector, which tells you right away that your matrix P is going to be I1, I, -1. And in order to finish the whole story, you need p to the -1, right? So let's find p to the -1. So how can we find p to the -1? Just use your equation. So p to the -1, the explicit formula. It's 1 over the determinant. What is the determinant now? The determinant is going to be minus I minus I. It's 1 over -2i. That's what the determinant is -2i, right? And then you put the numbers here in the same order. So -1. And then the other numbers, you flip them and you change their sign. So you put a -i here and the -1 here. What did I do? No, sorry, that's not right. I applied the formula incorrectly. My apologies. So first I put the -1 here, I here, and then I put a -i here and the -1 here. Now it's correct. Okay, sorry, that is. So now 1 over -i is actually I. 1 over -i is I. So it's going to give me minus I over 2, 1/2, minus I over 2, and -1/2. That's your matrix. Okay, so now we have the diagonalization equation, which looks like this. So we have -i over 2, 1/2, -1 over 2, no, I'm sorry, -i over 2, so this should be I, -1/2, times the matrix 1, 2i, minus 2i, 1, times the matrix I, 1, -1, is equal to the diagonal matrix 3, 0, 0, 1. That's the diagonalization equation. Okay, that equation establishes that the matrix is similar to a diagonal matrix. Questions, please. Questions? How did I get -1/2? So this -1/2 you're asking me. So pretty much in order to get that number, -i? What -i?
Sorry, I'm trying to say -I over 2.
Okay, I see. So basically, how did I get this? Okay, so how did I get this? So basically, I'm going to multiply this times that, right? So let's see how much this is. So -1 over 2i times -1. And basically what I said is, one way that you can think about it is you want to bring I on the top. So if you multiply above and below by I, what do you get? You get minus I over 2i squared times -1. I'm doing everything with a lot of detail. So -1 times the negative sign in front, that gives you 1. So you have I over 2i squared, and 2i squared is, and I squared is -1. So that's -I over 2. Okay, that's one way to see. And you know, it would be interesting to play around a little with this type of equations involving the imaginary unit. Okay. Now, I told you that I would show you how the Gram-Schmidt method is adjusted. The truth is that everything is done pretty much the same way. So if you have two vectors, let me do it for two vectors. So let's say that you had vectors u1 and u2. Okay, so v1 would simply be the normalization of u1, right? And now for v2, and this is why I gave you the formula the way that I did, so that it would look exactly pretty much the same as the trick here is that the vector v1 in the inner product has to be put in the second coordinate for this to work. So it will be, I'm sorry, u2 minus u2 comma v1 times the vector v1, and then you need to just divide by the norm of this thing, meaning you need to normalize. And that's how it works. So here the imprecise thing would have been to put v1 on the first coordinate. It wouldn't work this way. Yeah, this is where you know, one has to be careful. One doesn't have to be so careful in the case of the real vector space, but in the case of a complex vector space, one has to be careful like this. Okay, and that's it pretty much. So from this whole discussion, we will just hold on to the problem of the diagonalization of a Hermitian matrix, and that's all we're going to keep. If you look at the study guide, and let me just note here that you can now study the whole study guide. The exam is 2 weeks from today, right? But now you can prepare yourselves with a full study guide, with the exception of the very last problem. I'm going to explain the very last problem on Monday. But today, I'm going to give you a little bit of preparation for what we're going to do on Monday. So basically, I'm going to show you that many of the things that we have done can be done over completely different numbers. And those numbers actually, in the present day, turn out to be more usual in applications than the traditional numbers, or at least in one type of applications than the traditional numbers. And it's worthwhile seeing what situation that would be. So so here's what we're going to do. We're going to consider the case of finite fields. What is a finite field? So start with a prime number p. So let p be a prime number. Do we all remember what prime numbers are? A prime number is very good, and you just have to add something to it, that it has to also be greater than 1. So the number 1 is not considered to be a prime number. So a prime number is a number greater than 1 that is divisible only by itself and the number 1. So the first few prime numbers are 2, 3, 7, 11, 13, 17, 19, 23, 29, 31, 37, and so on. Okay, these are the first few prime numbers. So we define Fp is defined technically as the set of remainders upon division by p. And the remainders upon division by p are precisely the numbers 1, 2, all the way to p minus 1. So these are the remainders upon division by p. Now, here we have an interesting situation. So what do I mean by this? If somebody tells you divide 13 by 3, 13 is 3 times 4 plus remainder 1. So this is the remainder that I was talking about. Or if somebody tells you divide 20 by 3, this is 3 times 6 plus remainder 2, right? It gets a little trickier if you do it for negative numbers. Can anybody tell me what is the remainder when I divide negative 10 by 3? What is the remainder when I divide negative 10 by 3? You see, that's the everybody falls for that the first time. I already said that the remainders have to be from inside the set 0, 1 through p minus 1, so they have to be non-negative. So the only way to get a number in there is if you do 3 times negative 4 plus 2. Okay, so the remainder is actually 2 here. Okay, so there's this little trick for negative numbers. It's a good idea to remember it. Okay, so now what we do is we define addition and multiplication in FP. And the principle is as follows. So we find the result as usual. And if needed, we replace it by its remainder upon division by p. Okay, let me give you an example. Let's go to F5. Okay, in F5, how much is 1 plus 1? So first of all, let's recall that F5 will consist of what numbers? Of the numbers 0, 1, 2, 3, and 4. Right? These are the remainders that we need when we divide upon when we divide by 5. So if somebody asks you what is 1 plus 1, then 1 plus 1 of course is 2, and 2 is a perfectly fine answer because 2 is a remainder. 2 is in this set. So you can say 1 plus 1 is 2. That's perfectly fine. But if somebody asks you what is 3 plus 3, now things are different. Because 3 plus 3 is normally what? It's 6. Okay, we all know that. But 6 is not inside the set. So we replace 6 by its remainder upon division by 6. And the remainder of, upon division by 5. And the remainder of 6 when you divide it by 5 is how much? 6 is 5 times what plus what? Six is 5 times 1 plus remainder 1. So guess what? 3 plus 3 is 1. Okay. And can you do for me, please, how much will be 3 times 4 and 3 plus 4 and 2 times 3 and 2 plus 2 and 4 times 4. Could you please carry out these operations in F5 by using the same principle? Let's see if you can figure it out. Okay, let's see if you got them right. 3 times 4 is normally 12, but the remainder of 12 when you divide by 5 is 2. 3 plus 4 is 7. That makes it also 2. 2 times 3 is 6. That makes it 1. 2 plus 2 is 4. 4 is perfectly acceptable. And 4 times 4 is 16. The remainder of 16 when you divide by 5 is 1. Okay. Yeah, I know it's strange arithmetic, right? It's pretty strange. But I'm going to explain to you why this is so much intertwined with applications nowadays. I mean, one could easily say that what we're doing right now is more connected to actual applications. When I say actual applications, things that are being used right now as we speak, okay, as we speak. And you might say, come on, I mean, what we're doing a Zoom session right now. And I'm saying that these things are at work right now. Okay. Yeah, I know you don't believe me. But we'll explain how. Even though that's not the most important thing. The most important thing here is that it turns out that we can actually do division. And so for example, I can ask, what is 1/3? What is 1/3? And this is the wrong question here. This is the wrong question. What I should be asking is 3 times how much is equal to 1? That's what I should be asking, because that's what 1/3 is defined. That's what is defined as 1/3 in everyday life. 1/3 is the number that you multiply by 3 and get 1. So I could ask, in F5, which number do you multiply by 3 in order to get 1? And if you look closely, you already have the answer in front of your eyes. Does anybody see it? The answer is right in front of your eyes. What's the answer? 3 times how much is equal to 1? Very good. It's right here. It's right in front of your eyes. So in that sense, we're going to say that 3 to the negative 1 is equal to 2. And this implies, of course, that 2 to the negative 1 is 3. And then you can see that 1 to the negative 1 is, of course, 1. And 4 to the negative 1 is 4. Because 4 times 4 is 16, which is the same thing as 1. So we have addition, multiplication, and division. And the only time that we use that it's actually a prime number, because one could look at all this business and say, where exactly did you use the fact that it's a prime number? And the fact that it's a prime number is used exactly in establishing that we have division. Okay, that's exactly where we use it. And this is why we call it a finite field. I want you to send me a finite field, the term finite field as your attendance for today. And pretty much what we're going to do on Monday, just for one day, is we're going to see how we do linear algebra over finite fields. And you're going to realize, I mean, when I show you how we do linear algebra over finite fields, many of you are going to be like, why did we do linear algebra over finite fields from the very beginning? Why did we have to work over the real numbers? Because here's the thing, you never get negative numbers, you never get denominators. It doesn't get any better than this, right? It doesn't get any better than this. So of course, there has to be a much longer story of how these things were created. How did people wake up one morning and start creating those things? And if you look at the history of finite fields, you will understand that what is hidden behind it is the notion of congruence. The notion of congruence is exactly the process of identifying numbers when they have the same remainder with respect to a fixed number. And you will realize that the one responsible, quote unquote, for this theory is none other than, who do you think? The Prince of Mathematics, Carl Friedrich Gauss himself. Okay. So in any case, we will have a lot of fun with this. I would say, look at this type of arithmetic so that it doesn't look so strange. Matthews, where were you? No, it doesn't count the attendance now. Anyhow, I hope you have a great weekend, and I will see you on Monday.